This video is the second half of section 11.7 dealing with probabilities. All right, so we're going to start with talking about compound events. So example 5. So let's roll a fair six-sided die. So that's a standard die with sides 1 through 6. Let event A beget the event that you would get in an even number of dots to show up on the top of the die when you roll it. Event B is that 3 dots show up, and event C is that 2 dots show up. So using our set notation, we would say the event A has what elements in it? Well, let's see. So we're talking about an even number, so that would be a 2, a 4, and a 6. What would you put in the set B? So event is that 3 dots show up, so that would simply be a 3. C is that a 2 shows up, a 2. Now, if you remember set notation, that U stands for a union or an OR. So the event that A or B happens, so that would be the combination of these 3. Anything that's in A or B is included. If it's included in both, then we would not write it twice. We would simply write it once. So the A union B, or A and or B, would be 2, and I'll write them in numerical order, 3, 4, and 6. So even numbers and 3. All right, what about A union C? All right, so A union C, well, C is wholly a subset of A, so we wouldn't write 2 twice. We would just write 2, 4, and 6. So it's in one or the other, or possibly in both. All right, intersection, that's what this is. This means what are the things that are in A and also in C? Well, there's only one, and that's 2. All right, intersection of B and C, we're going to leave that empty. There's none. If we look at the Venn diagram here, this is a good way of looking at it. 1 and 5 are not in any of the sets, but event B has 3 in it. Event A has 2, 4, and 6, and event C has 2. So you can see the intersection of events B and C. There is no intersection, so we'll leave that blank. What about the intersection of A and B? And again, that would be left blank. There is no intersection of those 2 sets. All right, so what's the probability that A happens? So the probability that the event A occurs, which means you get a 2, 4, or a 6. So how many ways are there for A to happen? Well, there's 3 ways. How many different outcomes are possible? That's 6, or simply 1/2. Okay? Probability of event B, clearly 1 out of 6, and event C, 1 out of 6. All right, so what's the probability that you get A union B? So event A or event B. So we could think of this as unions in statistics generally mean or, and ors generally mean plus sign. So we could think of this as the probability of A or the probability of B. All right, and so what is the probability of A? Well, we saw that. I'm going to leave it as 3/6. Plus the probability of B, that was 1/6. So that ends up being 4/6 or 2/3. Now this formula for taking out the union and putting in a plus sign works really only when the 2 events are what we call mutually exclusive, and we talk about that down here in the notes. Mutually exclusive means that the intersection of the 2 events is empty, right? There is no intersection between the 2 events. The formula gets a little more complicated when there's an intersection. We're going to see that in the next example. So the probability of A union C, so if we use the same idea and we say, oh, that's the probability of A plus the probability of C, you'll see that that is not correct. Because if we look here, we know the probability, we can look at here, the union of the two has 3 events in it. So we know this should be 3 out of 6. But if we use this sort of newer formula that we were discussing, we would end up with something like 3 over 6 plus 1/6. So these are different, and that's a problem, right? And the issue is that this formula that we used over here worked because A and B are mutually exclusive. Here, A and C are not mutually exclusive. We can see clearly in the Venn diagram that they're not mutually exclusive. So if you want to use this formula, you really have to then take away the intersection. So we take away the 2 or the 1 option out of 6, and so that would take us back to the original formula. So we cannot use this formula here because of the fact that the 2 events are not mutually exclusive. All right, so the probability, the next one, probability that B union C, that would simply be B or C, right? So that would be the probability that you're in, there's 2 options for both of those, right? So that would be, where did we do B union C? Did we not do that up here? I guess we didn't. So B union C, well, there are 2 events, right? 2 items in both of those. So we know that this is going to be a 2 out of a 6, or reducing that to 1/3. All right, now intersection. So the intersection of A and B, well, that's an empty set, right? We saw that up here. So this is 0 out of 6, or 0. There are 0 outcomes in the combined event, so 0 out of 6. A union C, well, we looked at that up here, right? There is 1 item in there, so this is clearly going to be 1 out of 6. And then B union C, the probability of that happening, again, there is no intersection of those. We saw that that was an empty set, so there are 0 outcomes out of 6, or 0 is the probability. All right, so when we have an or a union of 2 events, and we're looking for the probability, then it's the probability of the first event plus the probability of the second event minus the probability of the intersection of those 2 things. Because, for example, we look up here, if I say the probability of A or C, and I say the probability of A, well, that's 3, because it's counting this 2 in the A, but this 2 also gets counted in the C. So the 2 got counted twice, so we would have to subtract away the intersection probability, or the 2 in that case. All right. For non-overlapping or mutually exclusive, the intersection, of course, is going to be the empty set, right? And so, therefore, the probability will be 0. That's why this one worked up here without that extra part of the formula over here, because A and B, those events were mutually exclusive. They did not overlap. All right. So let's look at some examples. So example 6. 1 card is drawn from a standard deck of cards. Remember, if you need to review that, go back look on page 2 of our notes that had the printout of all the different cards that are possible. Find the probability of the following. All right, so we draw 1 card. Probability that 1 card is a king or a diamond. So we can say, what's the probability that you have a king or a diamond? Let's just draw a diamond shape. And so that will be the probability that you draw a king plus the probability that you draw a diamond minus the probability that you drew some card that's both a king and a diamond. And if there are no diamonds that are kings, then this would be 0. But of course, we know there is one king that's a diamond. So how many kings are there? Well, there are 4 kings out of 52. How many diamonds are there? Well, there are 13 out of 52. And then we want to subtract. There is 1 diamond that's a king. Notice I don't reduce these fractions because I need common denominators in order to add or subtract those. So we end up with something like 16 out of 52 is the probability. And of course that we want to reduce. 4/13 is the probability of getting a king or a diamond. Now, I mean, sometimes it might be easier in some cases just to think about, well, how many cards is that? Like, add up this total right there. Well, there's 13 diamonds, and then there are 3 more diamonds. There's a diamond, hearts, clubs, and spades. So you can sort of add it up that way too by looking at your list of deck of cards. But this is using this formula. Okay. All right, B. The card is red or a king. So we're talking about the probability that it is red plus the probability that it's a king minus the probability that it is red and a king. So calculate that. All right, so the probability that it's red, well, that's half, but let's go ahead and write it as 26 out of 52 because I know I'm going to want to add fractions. And then probability that's a king, well, we saw that there in the last problem there are 4 out of 52 kings. And then how many red kings are there? Well, remember there are 2 suits that are red. They're hearts and they're diamonds. So there are 1 king of each in each of those. So there are 2 kings that are red, and so that's out of 52. And so combining all that, we get 28 out of 52. And of course, that reduces to 7 out of 13. So the probability of getting a red or a king is 7/13. All right, let's look at C. The probability that the card is a jack or a 7. So we do the probability. Let's just go ahead and follow that same formula that we saw up here. Probability that it's a jack plus the probability that it's a 7 minus the probability that it's a jack and a 7. All right, so the probability that it is a jack, well, there are 4 out of 52. Probability that it's a 7, there are 4 7s out of 52. Minus the probability that the card would be a jack and a 7, well, that's just not possible. So that would be 0. So this gives us 8 out of 52, reducing that down to 13th is the probability of getting a jack or a 7. All right, a card that is a red king. So it doesn't have it in there, but that's really the same as the probability that the card is a red intersection with a king. So both a red and a king. Well, in this case, we just think about how many cards that are. There's 4 kings, right? And how many of those are red? So that's just 2 out of 52. That reduces to 1 out of 26. All right, let's look at number 7. Suppose that 2 fair dice are rolled. All right, find each probability. So now some of you might say, well, what's the difference? But it's best if we list all the possibilities this way. In other words, what's the difference between, so 2 and a 1 and a 1 and a 2, aren't those the same thing? Yes, but if we think of these as one event rather than 2 separate events, then each event is going to have a different probability and it's harder to calculate. So it's easier if you think of, for the sake of calculations, one one dice is dark colored and one die is light colored, so you can sort of keep track of the two. So it's just easier to count the possible outcomes if you think of it this way. So as though the two dice are actually different. And so then we would end up with 36 different outcomes, as you can see here. Notice the doubles go down the aisle, okay, down the diagonal, I mean. And then also similar sums kind of go diagonally up this way. So these two add up to 4, these two add up to 4, and these two add up to 4. So get familiar with this. So for example, 7, these add up to 7, these two add up to 7, these two add up to 7, and so on. So diagonals this way have the equal sums, and then the diagonal going right down through the middle is the doubles, if you're interested in those. All right, so what's probably the first die shows a 5, or the sum of the two die is 11 or 12. Well, so let's write this out. So the probability that a 5 is first plus the probability that the sum is 11 or 12. And then what if it's both, right? What if both of these things happen? So we would have to subtract away the probability, and I'm just going to write, for the sake of space here, that both events happen. Okay, so if we think first, what's the probability that how many events? Each one of these events is equally likely. So any one of these, the probability of any one of these, this is like the sample space, right? So each one is equally likely, 1 out of 36. So how many of these events result in a 5 being the first die? So that would be this row here. This row has a 5, 5, 5, 5, 5, 5. It's the outcomes that have where the dark, in our case, the dark die, the first die, is a 5. And so there's clearly 6 of those. So this would be 6 out of the total possible 36. All right. How many ways can the sum be an 11 or 12? So think diagonally here. So this was 11, and this one's 11, and this one is 12. So it's really these items here. These 3 possibilities are both 11s or 12s is the sum. So that's going to be 3 out of 36. And then how many of these events? Both of these happen. So in this row and in that group. So it's just this one outcome here. So that would be 1 out of 36, giving us a total of 8 out of 36. Of course, that reduces 2 out of 9, dividing both of them by 4. 2/9 is the probability that that would happen. All right, so now let's try another one. The sum of the two die is at least 9. Okay, so let me erase some of my marks here so I can indicate which ones for this. Okay, the sum of the two die is at least 9. So think about going through the diagonals. Remember, this is 9, this is 9, this is 9, this is 9. So let's do that. So all of these down below are 9. So it's really all of these, because everything below that is going to be bigger than 9. So everything at least 9 or more. So how many events is that? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's clearly going to be just 10. So it's the probability that you have greater than or equal to 9, and that's going to be 10 out of 36. That reduces to 5 out of 18. All right, continuing on to page 4, we're going to talk now about something called a binomial experiment or binomial probability. All right, so for this first example, you have to understand a little bit about baseball batting averages. So in baseball, the batting average is defined by the number of hits divided by the number at bats that you had. It's usually reported as a 3 decimal place and pronounced as though it were multiplied by 1,000. So a player with a batting average of 0.300, that means about 30% of the time we would expect them to get a hit. But we say that they are batting a 300. right? So that's just how they say it, right? But it's really sort of a long-term probability. So if he has, over the course of his career, is batting a 300, that means he gets a hit 3 out of every 10 times at bat. So we're treating that as a long-term probability. All right, so example 8 then. If a baseball player has a career batting average of 250, or 25%, then he gets a hit 1/4 of the time that he is at bat. We can consider the probability that he gets a hit to be 1/4. If the same player has 4 at-bats during a particular game, then what is the probability that he gets exactly 3 hits? So we know that the probability of him getting a hit on any given at-bat is 1/4. And we're going to assume all those kinds of things are independent of each other, right? So if he strikes out the first time, he's not psyching himself out and then going to do poorly on the next at-bat. So we're assuming that each at-bat is independent of the previous or the next one. All right, so how many ways can we get 3 hits out of 4 attempts? So we're going to list those over here. So he could get, and we're going to use an H to indicate a hit and an X to indicate he did not get a hit. And there's a couple ways you could just not get a hit. You can foul out, you can strike out, you can do a pop fly. I mean, all kinds of other ways that you can not get a hit, but we're not going to go into those details. So he either gets a hit or he does not. So he could get a hit, a hit, a hit, and then the last at bat he could miss. Or he could get a hit, not a hit, and then a hit. He could get a hit, not a hit, and a hit. Or the fourth case, he could not get a hit the first time, but then get 3 hits the next 3 at-bats that he does. So there are 4 different ways of arranging 3 hits and 1 not hit in 4 attempts. All right, well, we're going to see in a minute how we could take a binomial and raise it to the 4th power, being the number of trials, or the number at bats in this case. And if we expand that out, it's going to help us do a bunch of different probabilities. Now, we only have one of these that we're interested in, but if we expand this out, it'd be helpful. So just to help us see, I'm going to write every coefficient with every term as well. So we have, if we expand this out, we have a 1, h to the 4, x to the 0. Normally we leave off that x to the 0, but I'm going to include it in this case. And then what would the next one be? Well, if you think about your Pascal's triangle, we know the next thing is going to be a 4, the next coefficient, h to the 3rd, x to the 1, plus, and then if you remember, go back and look at your Pascal's triangle, you get 6, h squared, x squared, and then we go back down to 4, h to the 1, x to the 3rd, and finally 1, h to the 0, x to the 4. And this device is really helpful here because ultimately what we're looking for is 3 hits and 1 miss. That's exactly what we've got here. A hit to the 3rd power, x to the 1st power. Because the probability with independent events, we're gonna multiply these probabilities. So the probability for this would be 1/4 times 1/4 times 1/4 times 3/4 for this to occur, right? So the probability that he gets a hit on the first one and a hit on the second and a hit on the third and a miss on the 4th, we would just be 1/4 times 1/4 times 1/4 times 3/4. But if you think about it for a second, the probability of this happening is the same as the probability of this happening, just in a different order, but multiplication allows you to do that. So the probabilities would be the same. Probability for each one of these calculations would be the same. So it could happen like this, or like this, or like this, or like this. Ors mean we would add them up. So we would have this plus this plus this plus this if we wrote all those out. And so we have 4 of those. So we have this probability, if we multiplied all that out, 1/4 times 1/4 times 1/4 times 3/4 times 4, or added it up 4 times, or multiplied by 4. So if we look at this and we let H represent the probability of success, in this case getting a hit is 1/4, the probability of failure is 3/4, and then the 4 in front tells us how many different possibilities there are. And so this is exactly what we want to calculate in our situation. We want probability of exactly 3 hits and 1 non-hit. There's 4 ways to do it, so that would show us kind of how to calculate it. And let's just think, this is another way of doing those coefficients, the binomial coefficients. Remember, go back and look at your binomial coefficient formula from a couple sections ago, and it would tell us another way, instead of using Pascal's triangle, another way of getting those things. Another way of looking at this too is, remember that there's a couple ways to write this. It's a combination of 4 choose 4, and we know that's 1. And this one would be a combination of 4 choose 3, and we know that is 4. Again, there's symmetry here. Down here, the combination of 4 choose 1, that is also 4. And then the last one, combination of 4 choose 0, and that is 1 as well. Usually these are in reverse. We start with a combination of 4 choose 0 at the beginning, but they're symmetry, so it doesn't really matter. So we get, this would be, and we might include here x to the 0 just to be a little bit more precise. There's only one way to arrange 4 hits, right? Hit, 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 hit. There's only one way to do that. But here we saw that there are 4 ways to do 3 hits and 1 miss. We saw that over here. There will be 6 ways of arranging 2 hits and 2 misses. There will be 4 ways to arrange 1 hit and 3 misses. And there are 1 way to get 0 hits and 4 misses, a miss, a miss, a miss, and a miss, okay? So you can fill those out if you wanted, but you kind of get the idea. All right, so what's this all boil down to, right? We're not going to expand this out every time. We really want to think about more the binomial theorem, which allows us to just look at one particular value, one particular term, because this is the only one we really need in order to solve this problem up here. So the probability of getting a hit when at bat, that's 1/4. Probability of getting a miss is 3/4. We've already kind of discussed that up here. So the probability of getting 3 out of 4 at bats, 3 hits out of 4 at bats, is just this. So it's 4 times, and then we have 1/4 to the 3rd times 3/4 to the 1, if you will. And again, we saw that that was the calculation here, but that's going to be the same for all 4 of those situations, hence the 4 in front. There's 4 ways to get that, and the probabilities would be the same regardless of what the order was in. All right, so this ends up being 3 out of 64. All right? All right, so now let's ask another question. What's the probability that this player, when at bat 4 times, gets exactly hit exactly 2 times? Well, that looks like this probability, right? So that's going to be, there's 6 ways to do that. And we have a hit, which is 1/4, raised to the 2 power, and 3/4 raised to the 2 power as well. I'm going to do that as, I'm just going to put that in my calculator, and that ends up being about 0.2109, or about 21% chance of getting exactly 2 hits. All right, what about at least 2? Okay, so at least 2 hits, that would be what? 4 hits would count. That would be also 3 hits, 2 hits. This would not count, and this would not count. So this one is going to be a little bit more complicated. It's going to be 1 times, and then, I don't know, we could go to decimals if you wanted, 1/4, which is probability, and that's to the 4th power. If you want just to be, clear, 75.75 to the 0, we normally would just leave that off in this case, plus, so it's this case, plus this, because if you think about it, this would be an or, right? So we could arrive at this kind of outcome by getting 4 hits, or getting 3 hits, or getting 2 hits. So it kind of makes sense that we're going to be adding these up. So this is 4, and then 0.25 to the 3rd, 0.75 to the 1, and then lastly, the last part, 6 ways to get 2 hits, 0.25 squared, and then 0.75 squared as well. And if you plug all that into your calculator, you get a 0.2617, or about, you might say, 26% chance that he would hit at least 2 times. All right. So for these binomials, how do we know that a binomial experiment is going to be appropriate here? So first of all, exactly 2 outcomes for every trial. So success or failure, right? So it's either he hit the ball or he did not hit the ball. We don't have a third option, he struck out, for example. 2 options only. All right, there's a fixed number of trials. So he has 4 at-bats, period. It's not, oh, he's going to keep going up to bat until he gets a hit, right? Because then we don't know how many at-bats he would have. So it has to be a fixed number of trials. The probability of success each time has to be the same. You can't decrease or increase that probability as time goes on. So we've got to think of his batting average up there as a long-term event. All right, and then each trial is independent. So if he strikes out the first time, human nature, we might say, well, he's going to psych himself out and maybe he would do worse the next time. We have to assume that each trial is independent and that the probability of each trial will be the same. All right, I'm going to run a little, attached to this video, going through a PowerPoint presentation for this next example dealing with a space shuttle. All right, so this is the example in our notes, example number 9, dealing with the space shuttle. It's a perfect example of calculating binomial probabilities. So a little background on the shuttle and how they put together a shuttle. So all the components get shipped down to Cape Canaveral, and then there is a building in which they assemble the shuttle and the external fuel tank and the solid rocket boosters that go next to it. They roll it out onto the launch pad and they fire it off. They launch it. And so after the launching it, the most of the thrust is achieved with the solid rocket boosters, those 2 long cylinders on either side. At some point after the fuel is spent out of those, they jettison those away. The external fuel tank is still attached to the shuttle at that point, and it continues to fire, and the jets on the back of the shuttle are the only thing propelling it forward at that point. But it's using the fuel in the external fuel tank, the big tank there. It's I believe it has liquid hydrogen in it. The solid rocket boosters is what we're going to concentrate on. Those get jettisoned away. They have parachutes in them that open up. They land in the water and they're reclaimed and taken apart, cleaned, and reused for the next shuttle launch. The external tank, at some point, the fuel's used up on that, and it's jettisoned off, and then, but it is not reclaimed. It's just lost, and they have to build a brand new one every time they want to launch the shuttle. All right, so we're going to concentrate on the issues that the solid rocket boosters had. So here's a picture of the solid rocket boosters just as they are being detached from the shuttle. They're spent. These are not built as one big long piece, but they're built as 4 separate pieces, and then they're sent to Cape Canaveral, where they're what they call assembled in the field It's not really a field, but it's not at the factory. They're assembled in the assembly building down at Cape Canaveral. All right, so they had a problem with their O-rings. So the O-ring, which is a rubber seal used to create a tight seal between two compartments, in this case two metal compartments, of the solid rocket booster. On the NASA Space Shuttle, so those things caused the Challenger disaster. If you remember, the Challenger was the name of one of the shuttles. I think we had 4 or 5 of them at one point. Challenger was the name of one of them, and it exploded shortly after takeoff. And that was on January 28th, 1986, long before any of you were born. I was actually a freshman in college when that happened. So in cold conditions, which don't occur very frequently in Cape Canaveral, Florida, down south, the rubber used to manufacture the O-rings can become brittle and possibly allow leaks. At the time the Challenger was last launched, the temperature was 28 degrees Fahrenheit, just below freezing. The coldest previous launch of a shuttle had been 53 degrees Fahrenheit, so substantially lower than what is typically the temperatures that's typically seen. All right, so here's a picture of them putting together the two parts of a solid rocket booster. You can see how large they are. You can see the people standing there next to it inspecting what looks to be the O-ring. But they're expecting it. Those are going to be, the top part is going to be lowered down and then bolted together, right? So a big, massive thing. So you can see here where the 3 joints are. There's this big O-ring that it goes all the way around each seal. Actually, there's 2 O-rings in the old design in each of those seals. So here is a picture of sort of the new redesigned after the failure of the Challenger. They redesigned how these 4 components get sealed together. But here is the old one. You can see the O-rings right here. There's 2 O-rings, rubber gaskets. These fuels are burning at a high temperature inside this thing, and this O-ring job is to keep it from leaking. And then when they're cold, the rubber tends to be a little bit more brittle and doesn't, it's supposed to deform a little bit and help seal the metal, the 2 metal joints. You see here some reclaimed, they reclaim these things, they refurbish them, and you can see how they have in past degraded quite substantially from what the cross section is supposed to be. All right, here is a time-lapse photography of the shuttle. You can see the arrow is pointing to the point where the flame is first starting to come out, and you can see in subsequent frames of the video, the flame is getting bigger and bigger and bigger, and so more and more of the O-ring rubber seal is failing and letting more and more of the hot gases to not come out the back of the thing, but out the side, and then eventually this thing just exploded. Those two trails going off into the top right of this photo are actually the solid rocket boosters just taking off haphazardly. All right, so let's look at the actual problem that we're asking you to look at here. So following the Space Shuttle Challenger disaster, it was determined that the failure of O-ring joints in the shuttle rocket booster was to blame. Under cold conditions, it was estimated that the probability that an O-ring joint, now that's 2 O-rings together making up 1 O-ring joint, would function properly 98% of the time. All right, so there are 6 O-ring joints. Each solid rocket booster is made in 4 big pieces, and then they're taken to Cape Canaveral and put together. So we would need 3 joints for each solid rocket booster. So that's a total of 6 joints. All right, so what's the probability that none of the 6 O-rings will fail? So the probability that 1 joint works is 98%. And the probability that it fails is 2%. All right, so how would we calculate the probability that all 6 work? Well, that would be just, or no failures occur, all 6 work. would be 0.98 times 0.98 times 0.98, 6 times, or just 0.98 raised to the 6th power. We'll see why, but let's kind of think of that as the probability of it working, which is what we're going to call W, capital W. The probability of failure, we'll call that F. So in this case, bear with me why there's a 1 there. It'll make more sense in a second. So we could write this as 1 times W to the 6th power, or W being the probability that an O-ring works. And since there's 6 O-rings, that kind of makes sense. All right, question B is asking, what's the probability that exactly one of the O-rings will fail? Well, this is a little bit more complicated. We could certainly calculate it looking at this, right? So 1 failure, which is 2%, times 5 successes, which would be each 98%. But that's assuming, of course, that the first O-ring, whichever one we're counting as number 1, that's the one that fails. It could also be this, 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 or this. So any one of those 6. So there's 6 ways in which one of these things can fail. So the probability of each one of these is the same, right? It's 5 successes and 1 failure. And in probability, whenever we're thinking about the word or, it's always going to be an addition. So the probability that the first one or the second or the third or the fourth or the fifth or the sixth fails would simply be the probabilities of each one added up. So in this case, it's easy to see that there are 6 possible outcomes. But in the next question, we're going to be asking, what's the probability that 2 fail? So it could be the first and the second O-ring joints that fail, or the first and the third, or the first and the fourth, or the second and the sixth, or the second. So many different possibilities when you start talking about 2 or 3 failures. Not that that's very likely to happen in this case, but still, we need a systematic way of counting that, and so combinations will come help us here. So the ways that you can choose 1 to fail out of 6 is the same thing as a combination of 6 choose 1. And so that will give us 6, and then times 5 of the successes and 1 of the failures. All right, so like we saw on the last slide, we have 6 times W to the 5th, and then F to the 1, knowing, of course, that W, it stands for the probability of it working, and F being the probability of failure. All right, so now 2, exactly 2. So we have how many ways of choosing 2 O-rings to fail out of the 6 possibility? Well, that's going to be a combination of 6 choose 2. Remember that 6 factorial over 4 factorial, 2 factorial, that ends up being 15. So there are 15 different ways of picking 2 of the 6 O-rings that will fail. If indeed 2 were going to fail, we have 15, and then we'll have W to the 4th, because there's 4 that work, and F to the 2, because there's 2 that fail. Well, hopefully you're kind of seeing a little bit of a pattern here, and let me help you see. Those just seem to be the terms of the binomial expansion W plus F raised to the 6th power. All right, so we can see that the coefficients of our terms, of our 7 terms, remember this is a binomial being raised to the 6th power, so we will have 7 terms, could be arrived at by using Pascal's triangle, or we could use the binomial coefficient formula involving our factorials to get each individual term, or the coefficient of each individual term. And then, of course, as we're used to, the W starts with a 6, exponent of 6 here, and then the next one has a 5, and then a 4, and so on, and then that decreases, and at the same time, F starts with a 0 in the first term, so we didn't include it. F has an exponent of 1 in the second. F has an exponent of 2 in the third, and so on. And so at the last term, it has an exponent of 6. So we know we have 7 terms. if we were to actually calculate all these, and we didn't in the last slide, so these are the actual numbers that I guess on our worksheet they're actually asking us to calculate the probabilities. We didn't actually write those down, we just wrote down sort of what the formulas would be. But if we look, and I continued to look at all 7 of them, I didn't include all the calculations here, I only included 5 of them. If we added all these up, the sum of all these terms, sum of all these probabilities would be 1, because there's only 7 possibilities. We have 6 O-ring joints. Either they all work, 1 fails, 2 fails, 3 fail, 4 fail, 5 fail, or 6 fail. So these are all of the possibilities, and so it makes sense if we add up all these calculations, we should get a sum of 1. Now that will come in handy in the next calculation that we do. Okay, so let's look at the last question they're asking us. On our paper, it asks, what's the probability that the shuttle would explode? So in other words, what's the probability that at least one of these joints would fail? Assuming it fails, if you've got flames shooting out the side of it, good chance that the whole thing is going to explode. So another way of asking what's the probability that it's going to, that the shuttle is going to explode is what's the probability that at least one O-ring joint fails. Now, if 2 fail, even worse, but really all we need is at least 1 to fail. All right, so we first want to look at this W plus F, that binomial to the 6th power. Like we saw on the last slide, we would certainly calculate all those out if we wanted. But what are we looking for? We're looking for the probability of at least 1 failure. So that means all the terms that have f to the 1, f to the 2, f to any power other than 0. So we're looking at those terms, right? The 6 last terms, everything but the first term. So now we can look at, that's a lot of calculations. It's 6 different calculations. Clearly the complement rule would be beneficial for us here. So if we do 1 minus no failures, probability of no failure, that would give us the same thing and be much more efficient to calculate. Okay, so that ends up being about 11%. So even though each O-ring joint has 98% chance of working properly, and that seems pretty high, when you think about the fact that there are 6 O-ring joints, and for successful launch of the shuttle, you need all 6 to work properly. So if you have, the probability that at least 1 fails is pretty darn high, 11%. Can you imagine, if you get in your car to drive to school and you have an 11% chance that your car would explode on your way to school, you probably would walk. All right, and finally, don't forget that you have homework 11.7.2. That'll be due next class period.